Hello everyone, welcome to another video. Today we have a AI image classifier. We're going to use Jupyter instead of PyCharm, which is better suited for these type of machine learning applications. So yeah, as you can see, this is the app. I'm just going to run it and demonstrate it for you very quickly. So the app is going to go over a data set of pictures, and we're trying to predict what is the picture, the actual picture. As you can see, the labels there, it shows the predicted and the true. So as you can see here, the predicted was cat, but the true picture showed a dog. So basically our app tries to guess the image that we're giving into it. Let's have a quick overview of what we're going to cover in this app. First of all, obviously we're going to have Python programming, machine learning, deep learning, TensorFlow, convolutional neural network, which is another topic of this video, CIFAR 10 dataset, which we use for our images, image classification, image data augmentation, neural networks, data processing, model training, and at the end, model evaluation. Yep, so this was a quick overview of our app. Not going to take so much time here. Let's just jump into the application and start coding. We're going to talk about it when we do that. Okay, so we launch our Jupyter and import few packages. First of all, we need TensorFlow, which is widely used for deep learning and neural networks. It provides tools for building and training models. Okay, so we're going to import from TensorFlow dataset, which provides access to standard datasets such as CIFAR 10. We're going to have layers, which contain predefined layers for constructing models, like convolutional layers and pooling layers. And at the end, we're going to have our model, which contain model types like sequential to build neural networks. And we're going to also import PyPlot, which is a library for plotting and visualization data. We're going to use it to display images. And the OS module, as you might know, provides function for interacting with our operating system, such as checking the file and stuff like that. And at the end, random, used to generate random numbers, useful here for picking a random image. If you don't have TensorFlow, you can go ahead and install it, pipe install TensorFlow, or the other packages as well, like PyPlot. You can just pipe install it, run this from here. I already have it, so I'm not going to do it. And I'm going to continue to the first stage of our application, which is load and preparing data. So as I said, dataset has CIFAR 10, which we're going to use for our today's application. Okay, train images and train labels, the training image and corresponding labels that we're going to have, that's what they are. And also the test ones are the test image and corresponding labels, which we're going to use for testing. And we're going to load CIFAR 10 from datasets, which contains approximately 60,000 32 color images in 10 classes, like airplanes, cars. The data set is split into 50,000 training images and 10,000 test images. That's what we're trying to do. Okay, in this line, we're trying to improve the performance of neural network. We're going to do that by normalizing the image pixel values to the range 0, 1, and we're going to divide it by 255, which is the maximum pixel value. This will help us to improve the performance of our network. Then we're going to go and have our classes, class names, which I'm going to pass here, okay, underscore. is a list of the names of the 10 classes in the CIFAR 10 datasets. These labels will correspond to the numeric labels in the train labels and the test labels that we have. So I'm just going to copy paste it. I don't want to type all of this. Then we're going to have model path, which will specify the file path where the trained model will be saved or loaded from on our system. Because we want to save the model once we run it for the first time. So the next time we wouldn't have to create it again and again. It just saves time and it's better practice. We go to path here. All right. We want to check if the path exists. So if the path exists, meaning we already have a model, we want to load that pre-trained model from the disk instead of training it again, so we can save time. So that's what we're going to do here. Load the model. We're going to pass it to model variable and model path. I want to print here that model loaded from disk. And if this does not exist, now where the fun begins. We're going to create the model. So we want to have a convolutional neural network, or CNN, using TensorFlows. CNNs are commonly used for image classification tasks, such as recognizing objects in images. This will create a sequential model, which is a linear stack of layers in TensorFlow. And these type of models are appropriate when your model consists of a single input, like an image, flowing through each layer to a single output. So yeah, we use sequential, and the first layer, it'll be conv which is a 2D convolutional layer. It applies a set of 32 filters, or kernels, in other words, to the input image. These filters will detect various features in the image, such as edges, textures, and stuff like that. So 32, which we have used here, is the number of filters used in the convolution. The more filters, the more features the model can learn. But also, this increases the computational complexity. So we need to be aware of that. And 3,3 is the size of the filters. It defines a 3 sliding window that moves across the image to detect features. And activation relo is the activation function applied after each convolution. Input shape specifies the shape of the input data. Here, the input is an image of size of 32 x 32 pixels with 3 color channels RGB. This layer is only used in the first layer to define the input shape of the model. Okay, next, we're going to have our second layer, which is max pooling 2D. It's a pooling layer that reduces the spatial dimensions like height and width while retaining the most important information. It helps downsample the feature maps and makes the model less sensitive to like small translation or distortion in the image. And the reason we use 2, 2 is the size of the pooling window. The pooling layer takes a 2x2 block from the feature map and retains only the maximum value. Okay, moving to our next layer. Similar to the first convolutional layer, we're going to have another conv 2D, but this time with 64 filters. This layer increases the number of models' ability to detect more complex patterns in the image by learning 64 different features at this stage. The filter size stayed the same, And activation function also the same as before. And then we're going to have another pooling layer to downsample the feature maps, again, reducing the size of the image representation. So let's go down here, max pooling to the, let me scroll down, all right. And you might have guessed this, but we're going to have another convolutional layer, again with 64 filters. At this point, the network has extracted several layers of features from the image. Now, deeper layers detected more abstract features like shapes or textures or patterns, stuff like that. And we're going to have a flattened layer, which will convert the 2D features maps, which are the output from the last convolutional layer, into a 1D vector. Flattening is necessary before passing the data into a fully connected dense layer, which we're going to have here. Also, it expects a 1D input where we're having a dense layer. And the dense layer is fully connected layer, meaning every neuron in the layer is connected to every neuron in the previous layer. And it consists of 64 neurons. And the activation would be the same. And at the end, we're going to have a final fully connected layer, consists of 10 neurons, each representing one of the 10 possible classes in the CIFAR 10 dataset. All right, we're done here, and we're going to compile our model. This will configure the model for training. So we're going to say model.compile. And inside of it, we're going to first have optimizer and pass to it Atom, which the Atom optimizer is used to adjust the weight of the neural network during training. It is an adaptive learning rate optimization algorithm. Loss function used to calculate the error between the model's predictions and the true labels. That's what we're going to do in this line. Before I forget, if you don't have Jupyter installed, go ahead and check out my Jupyter installation video. And I'm going to put a link right now up there. Click on it and check it out. So back to this line, we're going to have flag inside of it, which will indicate the model's output is raw and unnormalized, meaning the prediction haven't yet passed through softmax function, which is the loss function will handle the conversion to the probabilities internally. So you don't need to apply softmax before the loss calculation. Okay, next we need metrics for accuracy. Accuracy will be monitored during training. So let's have this here. Next, we wanna train the model on the training data. So we're gonna use something called fit model. All right, let's what's happening here? It's a little slow on my end. All right, yep. Let's go next line. Gonna have model dot fit. Then we're gonna have train image and train labels, which is the training data set. And we want to train the model for 10 iteration over the entire training data set. So we're going to say epochs equal to 10. And validation data is an argument that provides the model with the data that it does not use for training, but rather for evaluating its performance after each epoch. The test set, image, and their labels is used to check how well the model generalizes to unseen data during training, and it'll help detect overfitting early on. Now we have all that for our model. We want to save it. So we're going to say model.save, and we're going to pass the model path to it. And we want to save it in HDF5 format, so it can be loaded later without retraining. I want to print it here. And we're going to have a function called classify image. This will classifies an input image. So we're going to come down here. I'm going to say diff classify image. We'll also have another method called show image. Let's call it with prediction or something like that. It'll have two arguments, image and true label. And that function will display the image with its predicted class with improved visual quality. Yeah, so I'm gonna put it down here so I wouldn't forget the name. Image true label or true underscore label. All right, so back to our classify image. We're gonna have TF expand dims, which adds a new dimension at the 0 index to the image array, converting it into a batch of size 1, as the model expects batches of data. And predictions, which predicts the class probabilities for the image using the trained model. We're going to pass image array predicted class, which finds the index of the highest predicted value, the class with the highest probability, and convert it into a numpy or numpy integer. Yeah, I call it numpy. Prediction 0. Yeah, that looks right. .numpy, and I want to return the name of the predicted class based on the class index. Okay. Predicted class. All right. Let's go to our next func or diff. First, we want to predicted labels. I want to have that. Let's say classify image function and pass the image to it to get the predicted label. All right, so next we want to create a figure with reduced size to avoid pixelation. So PLT figure, fixed size, let's pass 2. So this will reduce the figure size. And then we want to display the image with no interpolation for sharper visuals. So I'm going to use I'm show actually. Show image interpolation nearest. And let's finish this, then go to the next line actually. All right, we want a title. So I want to set the title of the plot to show the predicted and true labels as you saw in the app demonstration section of the video. All right, predicted labels and true label. And let's remove axis from the label for a cleaner look. So PLT axis off. And at the end, we need to show. So we want to render and display the plot. So we're going to use plt.show. All right. So as I said, I want to randomly pick the pictures. So we're going to select the random index within the range of the test data set. So we're going to say length or len test images. All right, then we're going to have random image to retrieve a random test image. Random index. Now for the true label, we need to look up the true class label for the randomly selected image. So we're going to say true label, class names, test labels. And I'm going to pass to it the random index with 0. All right. Then we want to classify the random image using the classify image function we developed earlier. So class pred classify image. I'm going to pass the random image into it. And at the end, we want to show the random image with its predicted and true labels. So let's do that. All right. Image true label. All right, we look good. We're done here. Let's go ahead and run the app and see if we get any error, anything wrong with it, or anything like that. All right, before we run the app, there is one typo that I had. So as you can see here, this was not is, this was if. I made a mistake of typing is instead of if. You might have figured that out, but I just wanted to mention it if anyone is having any issues. Yep, just fix that and you should be good. And let's go back to running our app and see what's gonna happen. Yep. So predicted automobile, it's true. Good prediction. Because I already ran the app, so it loaded it this time from the disk. Deer, but the true was cat. So the reason there are incorrect prediction is because the model isn't fully learned the complex patterns in the data, and possibly due to insufficient training time or inadequate data. And it also could be because of the task difficulty. Misclassification can also happen because of the low resolution of the image, which limits the amount of detail model can learn from. But this is a basic model, so we don't want to go anything complex. We could have made it better at prediction, but that also raises other concerns like memory or the complexity of the computation. So we're going to stick with this app for now. And also about the photos, they may appear blurry due to their resizing or interpolation. Since the images are like 30x32 pixels, enlarging them more than this for display without proper upscaling technique can make them look pixel or blurry. I try to have it as good as possible. So if you make it larger, it would be more blurry. So yeah, that's the reason for the blur images. But for the purpose of our application, that is good enough. We don't want it to develop a very complex model, just a basic one to work around with the image classifier app. And yep, that's it. This is the end of our application. I really hope you enjoyed watching this video, guys. If you did, please go ahead, give me a like, subscribe, or any comment, any ideas for the next video, anything that you would like to share with me. I would really appreciate that. Again, if you like this video, don't forget to hit the subscribe button. Thank you and have a great day.